I'm Dr. Amanda Fetch. Welcome. I'm excited to share that my dissertation, Advancing Space Situational Awareness Through Density-Based Clustering, Utilizing Machine Learning Technology. Yes, I know it's a mouthful. It's now officially available on ProQuest and Google Scholar. And so in this video today now, I'm going to start to walk you through what I researched at a high level, almost on a chapter by chapter basis, and why my research matters and why it's more important than ever. Now, starting out with chapter 1, intro section, and I sort of lay out the landscape and why this is even an issue. So I start by introducing this growing, almost like a crisis in orbital debris. Now we have over 9,300 tons of material that's floating around in orbit. Pieces of satellites, paint chips, whatever it is, right? From these, sort of broken off things, for a better word, off of satellites and things like this. And there's tens of thousands of satellites planned to launch over our next decade. And so the congestion happening in Earth's orbital environment is now evolving into a national security and an operational threat for everybody. And so if you haven't had a chance yet to check out my video on space situational awareness. But SSA tools, very robust, existing out there in the market, in the environment, they're overloaded right now. So there's this critical gap of existing systems that are struggling to efficiently prioritize which debris is actually posing the most threats before they're even fed into things like a conjunction algorithm for a risk assessment and things like this. So my research proposes using DBSCAN, which is a density-based clustering algorithm. Again, if you haven't had the chance, check out my DBSCAN video on this. You can get a deeper dive. Basically, it's a machine learning pre-processing method that helps flag anomalous objects, better organize space object behavior before we have sort of any deeper analysis. Again, before you would feed these objects into a conjunction algorithm, for example. Now, chapter 2, my literature review, talk a little bit about the evolving of these systems, some key gaps and things like this. So I start with almost a historical and a technical review of those systems and how they've evolved, again, in response to this sort of growing problem of space congestion and major orbital events. And so my work starts off by tracing the evolution of SSA, from early defense initiatives to modern AI enhanced systems. And so very high level brief timeline. We had things like in 1957, launch of Sputnik 1. Now we started to create the first human-made debris. Then in the 1960s through the 1990s, we have tools like Project Space Track, Sputnik, so SPADOC, Navy Spacer, SPA, SUR radar network, laid the foundation for object tracking. Then in 1978, many of you who study space know about the Kessler syndrome. So now it's just sort of introducing a cascading risk of orbital collisions. 2007 to 2009, we had events like China's ASAT test and the Iridium Cosmos collision, which added thousands of new fragments floating around out there. Now in the 2020s, we have the rise of mega constellations like Starlink, emergence now of AI and ML enhanced SSA tools. And so now we have this sort of evolution that's creating this more urgency for modern data-driven processes and techniques to help categorize orbital debris more effectively than what's been done in the past. Now we have major space agencies that are on this, right? So we have your big players, NASA, ESA, IADC. They're central to global efforts in advancing SSA, mitigating this space debris crisis. Now, each agency contributes different unique capabilities, of course. So, again, this is kind of my opinion, which some of my research led to. So, NASA, I'd say, kind of leads in a conjunction assessment and debris modeling. Okay, through tools like CARA, so the Conjunction Assessment Risk Analysis, that team, ORDEM, Orbital Debris Engineering Model. ESA, on the other hand, they have their Space Debris Office. They employ tools like the MASTER model. They manage data sets like DISCOS to evaluate debris risk, predict environmental evolution, things like this. Then we have international forums like the IADC, that are helping to set shared guidelines for debris mitigation and coordinate technical collaboration across nations globally. Now, in terms of tools and algorithms, My research went in and highlighted quite a few, so I'm just going to touch on a couple of them now, high level. So tools like CARA, okay, conjunction assessment systems and tools, uses things like high fidelity orbital data to screen for potential collisions. Okay, they're assessing risk levels, they're recommending maneuvers. Now, STK conjunction analysis tool, CAD, okay, further refines predictions. Now you're pre-filtering orbit data, you're visualizing risk zones. You might be using things like dynamic 3D ellipsoids. Okay, these tools depend heavily on accurate data. Okay, they're supported by technologies like the Goldstone radar, which is tracking objects in deep space. Haystack, so we have the Haystack Ultra Wideband Satellite Imaging Radar, HUSIR, okay, and tracking of small debris, okay. Now we have orbit determination. So my study looks at classical algorithms, Gauss, Laplace, Gooding, different algorithms. Each have their strengths, they have their weaknesses, right? Everything does. So for instance, Gauss's method, it's geometry based, struggles with straight line motion. Okay, Gooding's method provides a little bit better convergence for complex trajectories. I also researched, or I quoted a study, or I should say cited is a better word to say it right, wasn't quoted. I cited a study by Zhang et al. 2024, okay? Basically is exploring how space-based optical platforms using these algorithms can improve SSA accuracy by avoiding atmospheric distortion, enabling longer tracking windows. Okay, so there's some really awesome studies that I cited in my literature review you should check out. Now, on the tracking and monitoring front beyond ORDEM, BUMPER, okay, is used to assess micrometeoroid and debris impact risks on spacecraft, supporting mission design, safety planning. So now these models are relying on data sets like the Space Surveillance Network, SSN, and spacetrack.org, which is what I used in my research. And they're basically cataloging orbital objects and are used for predictive analytics and things like this, or in my case, machine learning clustering. Now, also looked into numerous debris mitigation technologies. Okay, so for things like active debris removal, so ADR, we have things like Gossamer Orbit Lowering Device, GOLD. Okay, multi-spring damper nets. Those are designed to deorbit or capture debris. We have technologies like net capturing, inspired by almost like a fishing net mechanism. Now they're able to entangle debris mid-orbit. Now we have operational demonstrations like remove debris, that mission aimed to demonstrate technologies for removing space debris. It was carried out. Main satellite deployed from the ISS to the International Space Station. This was done back in June of 2018. Various experiments were conducted. They included net capture, harpoon, and other tests and things like this. So again, different technologies, missions that I had analyzed within my literature review. Now we have things like DRISS-J, okay, active debris removal by astroscale, okay, out of Japan. That was launched in February of 2024. And what that one looked to do was to demonstrate the feasibility of inspecting and potentially H rocket upper stage removing space debris and things like this. So if you want to dig a little deeper into that, please, again, check out my study in the literature review section. Now, the basis of this, without getting too deep, again, I wanted to go very high level on this. Together, these tools and these technologies and these global collaborations sort of provide the foundation for advanced SSA methods and technology. And what we're trying to do here is to improve risk assessments, ensure that Earth's orbits remain unstable. I shouldn't say that. We don't want them to remain unstable. We want them to remain usable. We want them to remain usable for future generations, okay? Because it's going to get so packed out there, we're not going to be able to use it, okay? We're going to start deeming these things sort of unusable, easiest way to say it. Now, this starts to lay the groundwork for my methodology, okay, and where I use DBSCAN and applied it to the orbital data set, which again, I use spacetrack.org data set, which is maintained by the US 18th Space Defense Squadron and SAIC. So my study was quantitative and it was exploratory by design. Now, what that allowed me to do was have both a statistical depth and a pattern discovery going on there, which is important when you're dealing with massive and complex orbital data sets. Now, it's important when you're doing any research study. So for the PhDs out there, you already know this. Others who might not be as deep into this, And also I have a master's of research I did before this, so it really kind of got into my head here. Research has to be adaptable, reproducible, and transparent. Okay, so that others in the space community can replicate my method by using open data, making this more accessible, making it accessible for future academic or operational usages. That was one of my main goals. Now, methodology, I've said this multiple times, I gathered data from spacetrack.org, focused on large trackable debris, 10 centimeters and up. Now I use the CCSDS standardized format. I'm not going to dig too deep into that now. That's something I could talk about in other videos, or you can pose it in the question if you're curious what this means. Again, this is a high level of what I did for my study. Now for the clustering process, I relied on Keplerian orbital elements. What that means is I use variables like eccentricity, inclination, right ascension of the ascending node, argument of perigee, okay, mean anomaly, and other elements. Now, why did I choose those? Choose those because they pretty much give us a pretty clear picture and fully describe, I would even argue, the shape, orientation, and position of an object's orbit. Now, it makes them ideal for identifying patterns in orbital behavior then. Now, since clustering is sort of all about finding structure in data, have to use parameters that inherently define this object's orbit and gives the algorithm something meaningful to work with. Now, from there, once I chose the parameters, moved into data cleaning, pre-processing, scaling, normalization, correlation analysis. That's when we went back in, regrouped, and maybe eliminated some parameters. Okay, so after the correlation analysis, k-distance plots, help to select optimal parameters for DBSCAN, also grid search. Now I'm going to touch on those things in another, sort of later video and things like this. Now grid search is what I use to test different epsilon and minimum point values. These things can be infinite, okay? So there's ways to figure out starting points. I looked at validity. Internally, through careful parameter testing, consistent pre-processing, lends itself back to the grid search process. External validity, using well-established data sources aligning with CCSDS standards. Now that ensures relevance and ensures transparency. If you're working in AI now, that's all you're hearing. Explainability and transparency. Same goes for the research world and research process. Now, moving on, chapter 4. Good stuff, results, clusters, noise, behavioral patterns, things like this. Analyze the outputs of my DBSCAN algorithm. Now, I'm not going to go in too deep of what I found. Okay, that can be for another video. What I would also say is this is to be taken with a grain of salt because as your data shifts, findings are going to totally shift. The importance of this was the framework I developed. Now, high level, we had baseline of behaviors, specialized patterns, and again, going back to sort of noise or anomalies. That was the basis of this. So that could be like outliers. Doesn't necessarily mean maybe they're high risk, but they're behaving differently from this baseline of behavior, from other specialized patterns, things like this. So the findings section now, so kind of to bring everything home in the final chapter of my research and in this dissertation you're going to find, if you check it out. Final chapter is where I introduce the framework. Okay, now the framework was called the DBSCAN Cluster Prioritization Framework. Now what it's designed to do is help, if you're a stakeholder in SSA, use this to basically do a pre-processing again on the objects you should focus on first for these sort of conjunction assessments and things like this. So before you can do any of this, you have to establish your baseline of behavior. Something that could be more predictable, okay, structured. You're going to use it to reference everything else. It's how you're going to know something's an anomaly or something specialized, okay? Now, specialized patterns, distinct behaviors. Okay, we might need to customize tracking in this way or customize our mitigation practices. Now, anomalies we want to pay attention to. They're irregular. They could be our high-risk objects. We don't know that yet. This is a pre-processing, remember. So this is something we want to keep our eye on. We probably want to feed them in first, but that doesn't automatically mean they're going to like cause the end of the world or something like this, right? These are just things we should look at, sooner than later, possibly to assess that risk better. Now, what this is doing is this research serves as a pre-processing layer for tools like CARA or ORDEM by filtering incoming orbital data and assigning levels of concern and risk before we even do a full-on risk, okay? Now, the reason of this is now we're tracking thousands of pieces of debris. We're going to get to the point where we can track the millions that are floating out there. And it's just too much to handle in algorithms and things like this when you're ingesting 128 million pieces or whatever it is of debris and you're looking at it individually. It's just too much. So this is a way to sort of cluster this stuff together and look at it in a more organized fashion, okay? Now, with that being said, in my last chapter, for those who aren't necessarily space fanatics, I looked at other ways to use anomaly detection and pattern recognition in other areas and industries. So I'm not going to drop that now. It's something you can check out if you're interested. I'll let you go ahead and do that. So again, full dissertations now published on ProQuest and Google Scholar. And one more time, it is advancing space situational awareness through density-based clustering, utilizing machine learning technology. So if you're involved in the aerospace industry, AI, national security, whatever it might be, or you just have a passion for this stuff, you find orbital debris fascinating, maybe you're tracking the satellites that are going up into orbit, whatever it is, I encourage you to go ahead and take a glance at this. And one thing I will say, not to just pat myself on the back, I really tried to make this digestible for all audiences. So don't think if you're not some sort of AI engineer or things like this or a deep machine learning scientist, you can't read my dissertation, because I made it so that it's very digestible for diverse groups and audiences. So please, definitely check it out. Let me know what you think. Let me know if you can apply it in your area and industry. And, again, love to discuss. So take care and thanks for tuning in. I hope you'll check out my dissertation and enjoy.